second system on a rig is the hoisting system. Basically, this system raises and lowers the drill pipe of the drill stem in and out of the hole. It suspends the heavy weight of the entire drill stem in the hole, a hole that can be 5,000, 10,000, even 20,000 feet deep. Raising and lowering that drill pipe hundreds of times before the well is completed, it must be strong enough to handle very heavy weights. As I said earlier, there are essentially 5 major parts that comprise the hoisting system. They are the derrick, the drawworks, the crown block, the traveling block, and the hook. Let me explain their functions. The first is the derrick or mast, the most distinctive part of the rig. It is a structural tower that suspends and supports the hoisting system and pipe. It must be tall enough to pull a 2 or 3 stand or length of pipe of up to 90 feet out of the hole at one time, and also strong enough to support the entire weight of the thousands of feet of drill string below. Let me show you the hoisting system in operation. Here we have the drawworks. It controls the drilling line or steel wire rope that goes from the drawworks drum on the drilling floor up through the crown block, then down to the traveling block where it is attached. As you can see, the drawworks is a large rotating drum that spools in and out the drilling line as it is raised and lowered with the load, which is usually the pipe. The drilling line runs up the derrick to the crown block, which is another component. As the name implies, the crown block sits at the very top of a derrick like a crown. Steel wire from the drawworks is threaded through the crown block in assembly of multiple pulleys called sheaves, which increase the steel wire's load-bearing capacity. The number of these pulleys is dependent on the needs of the drilling program. For example, deep wells require more pulleys than shallow wells because of the weight from the extra drill pipe. Next, from the crown block, these multiple strands of steel wire are attached to the traveling block. Together, the fixed crown block and the moving or traveling block gives tremendous mechanical advantage for hoisting very large loads from the hook, which is located below the traveling blocks. With these 5 components, the hoisting system can raise and lower the drill bit and its string in and out of the hole. Before we leave the hoisting system, let me mention some components of pipe handling. The specific tools used when raising and lowering pipe into the hole are the elevators, the slips, and the tongs. Specific places on the rig involved in pipe handling are the fingerboard, the rat hole, and the mouse hole. Let me explain these in more detail. The elevators are attached to the hook and are used to lift the pipe string. Second, the slips are used to hang the string from the rig floor. The tongs are used to make up and break out the pipe stands. These power tongs can spin the pipe while the backup tongs keep the rest of the string from turning. The fingerboard can be found high up on the derrick and has protruding fingers that can hold stacked stands of pipe. The rat hole is the hole in the rig floor where the Kelly and the swivel are stored when they are not in use, and the mouse hole, like the rat hole, is a hole in the rig floor. The mouse hole is a place where a joint of pipe can be placed prior to it being added to the string. Altogether, the hoisting system supports the drill bit with its lifting and lowering capabilities. The third is the circulating system. Introduced quite early in the evolution of drilling technology, it is the backbone of the rotary drilling. In this system, mud is continuously circulated down the drill string to the nozzles in the bit and then back up to the surface through the annulus or space between the drill pipe and the hole. This circulation of mud has several functions. Number 1, The first function of the circulating system is to lubricate and cool the rotary blades as they bite into the rock at the bottom of the hole. This helps to greatly extend the bit's useful life. Number 2. The mud jets in the bit flush the drill cuttings away from the bit itself, thus cleaning the rock surface and allowing the bit to penetrate more efficiently. Number 3. The mud collects the loose rock and dirt and brings it back to the surface through the annulus and up out of the hole. These pieces of loose rock and dirt are called cuttings. Number 4. Throughout this process, the mud exerts back pressure on the exposed formation, thus preventing an influx of formation fluids called a kick, which could cause a blowout. In other words, the mud helps to maintain the pressure in the hole to help prevent blowouts. This pressure is called hydrostatic pressure, and it is imperative to keep the hydrostatic mud pressure equal to or slightly greater than the formation pressure. By the way, when the hydrostatic pressure is greater, it is called an overbalance. When the pressure is less, it is called an underbalance. We'll talk more about overbalance and underbalance pressures later. Number 5. Finally, the mud reduces friction between the drill string and the side of the hole. Because of cost, the most commonly used mud system is water-based with various additives. In more technically challenging drilling programs, where greater stability justifies its additional cost, an oil-based mud or water in oil emulsion may be used. In offshore wells, where disposal of drill cuttings overboard is restricted because of environmental concerns, even more costly synthetic chemical muds are used. Because of the above reasons, mud engineers and mud loggers constantly monitor the mud's characteristics and make changes as needed. The main way of changing the downhole hydrostatic pressure is by controlling the mud weight or its density. Here is an illustration of the circulation system located next to the rig. As the mud comes out the annulus, it is diverted away from the rig floor into the mud return line, which takes the mud to the shale shaker. The mud falls through the shale shaker, which has a calibrated mesh that screens out the large cuttings. These cuttings are examined by the site geologist to determine rock type. The large cuttings then go to the reserve mud pit for disposal. The mud, following multiple steps, then flows back into the mud tank to be recirculated down the well. Finally, I want to mention briefly a new drilling technique for controlling downhole pressure that is rapidly becoming widespread. It is called Managed Pressure Drilling, or MPD. Let me explain why it is quickly replacing the conventional method. Traditionally, to control the bottom hole pressure, the density or weight of the mud was changed. For example, if a driller needed a greater downhole pressure to control a kick, he circulated down a heavier mud. In managed pressure drilling, this is no longer the case. Now, the driller no longer needs to stop to change the mud weight. He can now just change the annulus pressure and the inside drill pipe pressure to increase or decrease the bottom hole pressure, thus eliminating the time lag for changing the mud weight, resulting in faster drilling times, fewer kicks, and fewer stuck pipe incidents. It is easy to see why MPD is quickly becoming a preferred new drilling technique. The fourth system on the rig is the prime mover. The prime mover is the source of power for the entire rig, which is diesel electric. Using diesel engines to drive electric generators, these generators produce direct current to power the rig's hoisting, circulating, and rotary systems, as well as all of the other electrical equipment used on the rig. On large rigs, it is common to have backup generators for emergency power failures. The last is called the pressure control system. Its principal component is the blowout preventer, or BOP. Bolted to the top of the well and located below the derrick floor or on the ocean floor offshore, BOPs are used to close off the top of the well in the event of a large pressure buildup that could lead to a blowout. A blowout is when reservoir fluids blow up out of the hole onto the rig floor. This force can be so powerful that it can smash tools together and where a spark could ignite the fluids, causing an out-of-control fire that can burn up everything in its vicinity. The BOP is operated from a control panel on the drill floor. Because of its importance in stopping a potential life-threatening and environmental disaster, the BOP even has its own independent power supply. It has been determined that one of the reasons for the disastrous and costly Macondo Gulf of Mexico oil spill in 2010 was the result of a faulty blowout preventer which did not stop oil from flowing into the ocean as designed, causing loss of life and costing billions of dollars in cleanup. This disaster highlights the importance of monitoring and maintaining a fully functional BOP during the entire drilling program. Let's look at how a BOP, a blowout preventer, works. To ensure that reservoir fluids do not get into the wellbore, the driller pays close attention when drilling into porous, permeable rocks where fluids can be under pressure. Therefore, when the reservoir rock is drilled, it is vital for the reservoir pressure to be offset by the mud pressure. As I mentioned earlier, mud pressure reflects the hydrostatic head of the column of mud in the hole above the formation. This downward force of the column of mud is expressed in pounds per square inch, or PSI, which indicates how much weight is pressing down on 1 square inch of area. Mud pressure increases with the depth of the hole and the density of the mud. Let's look at an example of how to measure that pressure. Mud pressure at the bottom of a 7,000-foot hole filled with mud having a density of 10 pounds per gallon can be calculated as follows in a hydrostatic gradient. In this illustration, we have a column of mud that is 12 inches by 1 inch by 1 inch, weighing 0.51 pounds. First, we'll convert the gallons to cubic feet. Then, we'll divide by 144 to get the weight of each 12-inch by 1 inch by 1 inch column within the cubic foot. This is the hydrostatic gradient showing the increase of pressure per inch per depth. Next, we'll multiply the per foot hydrostatic gradient by the depth to get the mud pressure at the bottom of the hole. In this example, therefore, our PSI is 3,605. Since the reservoir pressure in this example is over 3,500 PSI, we say that it is overbalanced. This means that the mud pressure exceeds the reservoir pressure, causing mud filtrate to invade the formation. The solids from the mud filter out on the face of the formation, which forms a filter cake. If the reservoir pressure were higher than the mud pressure, say 4,000 psi, this underbalance would cause the formation fluids to enter the wellbore in a condition known as a kick. If this happens, then aggressive action must be taken to prevent a blowout.